In this video, you're going to learn about industrial IoT connectivity technologies such as OPC UA, data distribution service, MQTT, CoAP, 1M2M, and more. We're going to focus on the fundamentals of industrial internet, the industrial internet connectivity stack, why connectivity technologies do not overlap, and why connectivity wrappers do not work. And my guest to help share that knowledge is Stanley Schneider. Stan is the CEO of Real-Time Innovations, or RTI, which is the world's largest software framework provider for smart machines and real-world systems. RTI software runs over 1,500 designs, including the largest power plants in North America, the Canadian Air Traffic Control System, NASA's Launch Control System, nearly all Navy ships, GE Healthcare's hospital device networks, Siemens wind turbine farms, trains and metro control systems, and over 250 autonomous vehicle designs. Stan holds a PhD from Stanford in electrical engineering and computer science with a focus in autonomous systems. Welcome to the fourth generation podcast here on Industry40.tv, which is a series of weekly interviews designed to help you learn industrial IoT from some of the world's leading practitioners. So make sure to subscribe and click on the notification bell to make sure that you never miss any of the interviews. If you find this conversation interesting, please review it with 5 stars on Apple Podcasts, follow on Spotify, and connect with me on LinkedIn at Kutsai Mandi Teresa. Now, here's my conversation with Stan. Stan, thank you so much for joining us today on the show, and welcome.
Okay, thank you very much. It's great to be here and
Okay.
nice to meet you today.
Great stuff. Okay, so yeah, I think we'll just dive right into it. So now, Stan, the ability of systems to communicate really is like the most important aspect of industrial IoT, and that's probably the reason why we've seen many connectivity technologies being developed over the years. Now, to help system designers understand and choose the right standard, the Industrial Internet Consortium, which is an organization of which you are a member, came up with the Industrial Internet Connectivity Framework. Okay, so could you describe to us what the Industrial Internet Connectivity Framework is all about?
Yeah, so back when the IoT was young, this was 2014 or 2015, when the IIC was founded, we realized one of the big problems is people just didn't understand all the different protocols. I put protocols in quotes because calling some of these technologies protocols isn't very fair at all. And so we set off on a project to better understand them and, more importantly, help people understand when they should use different ones. And that was an interesting journey, to say the least. So we ended up looking at 6 different things: so DDS, OPC UA, RESTful HTTP, MQTT, something called CoAP, and we wanted to really understand how they what they actually did, and how they another thing called 1M2M, which is a different kind of technology, really. What they really were, how they interacted, if they interacted, maybe a vision for the future, how they could all work together. And when we started out, I actually wrote a paper and got it published in a journal about how all these different technologies overlap in different areas, and we put together a 10-dimensional space of things you should look at, like latency and bandwidth and scalability and all these kinds of things. And I thought that they would overlap, and you would, narrow it down to a couple of different technologies and then choose them based on some other thing like cost or performance or something like that. And what we found out instead is that these technologies are amazingly different. They evolved out of completely different environments for completely different use cases, to the point where we even had a problem just classifying them as types of technologies. So we basically ended up with a new stack and a new sort of way to think of a way to think of how you build an architecture. I won't even call it for connectivity, but for a distributed system. And I sort of come to the conclusion there's really three different kinds of distributed systems. IoT is not one thing. Internet of Things, unless you want to call it the future of all technology, which is a bit much. It's not one thing. It's three things, my humble opinion.
Okay.
And the first thing we call device monitoring, which is really a single device. You could have a lot of them, but a single type of device talking to a single cloud service. And that's all it does. So think, Nest thermostats and Ring doorbells, and there may be different kinds of Ring. There's Ring doorbells and Ring alarms, and lots of different devices like that. But they all talk to one cloud service, and they don't do much else. So from a connectivity architecture point of view, it's very simple. It's just a one-to-one connection. So that's the first class. The second class is very different. You take a big existing plant or an oil pipeline or some big system like that, and you put sensors all over it, and you collect those sensors up in the cloud and do some kind of analysis, maybe a big data analysis or just display for people. And we call that analytic optimization, because what you're really trying to do is analyze what's going on in an existing system. You typically don't change that system. Small changes, you're instrumenting a power plant or something like that. Big market. You'd think it would be the first market. The entire consumer internet is in the device monitoring market. Most of the big companies went after this analytic optimization market because you can immediately install it on existing plants, and that makes it a big market. So you'll think, Siemens MindSphere and what used to be GE Predix and is now just Predix. Somebody else bought it, and most of the technologies out there really fit into the second category, which is all about getting data and being smart about that data. And then there's a third category that I think is the most exciting, but the least mature, which we call edge autonomy, which is basically taking artificial intelligence out of the cloud and making it work in the real world in a way that it doesn't work today. And the applications you've heard of here are things like autonomous cars and, what else might you have heard of? Flying cars and, but there's many other kinds of things. That's where my company exists, is really in the edge autonomy, and we do everything from forklifts to trucks to wind turbines to medical device integration to robotics to intelligent fish farms. And it's just a very big array of things that you can add intelligence to AI, not in the cloud, out in the real world, and make a smart distributed system. So you sort of have to understand that. And then you look at these other technologies, and we split them. We built a stack that's based on interoperability rather than based on the very simple descriptions of the enterprise stack, which is, there's a famous thing called the 7-layer model. The first 3 layers are really just how you get bytes around, and that's fine. We didn't change any of that. But above those layers, we try to look at what's really important. And what's really important in this world comes down to interoperability. And what's important about interoperability is what's interoperable. So the word interoperability is a very popular word in the Internet of Things. You'll hear it every paper, everything we talk about. I don't like the word without the word between after it. So interoperability between devices and a network is a very different thing than interoperability between software modules and a big design is a very different thing between interoperability between machines on a factory floor. And they're just completely different concepts. So we try to, we're just looking at the networking and really architecture. We sort of define 3 levels of interoperability, which is technical interoperability, which you can share opaque blocks of data, and syntactic interoperability, you can share data types, and then semantic operability, you can share meanings of data types. Anyhow, it's a long answer to your relatively simple question, so I'll back off now. But we really had to completely redesign. The framework designs a whole new stack, and it also goes in and analyzes all these technologies and proposes a potential future where we can connect them together where we would need to.
Okay. Yeah, so when it comes to the IoT connectivity technologies that we've just described, you like in your book, you stress your book, the rise of the robot overload. You stress the point that these IoT connectivity technologies do not overlap. What do you mean exactly when you say these technologies do not overlap, and what are the implications of that fact?
Simply put, I have yet to see any significant applications that you really could choose one or the other and it makes sense. The problem you have is not deciding which one to use for an application. The problem is understanding what your challenge is, and then choosing the one. Usually only one. If you have a very simple problem, maybe you can use whatever, but choosing the one that will work. My favorite analogy is with transportation. And you could argue that transportation technologies overlap. A train and a car and an airplane and a bicycle and your shoes are all transportation technologies. And they all, if you're just going, if a simple use case, you're going from your house to work and it's close by, well, the plane might not work. But the other ones, if it's a few kilometers away, you could ride a bike, you could take a train, you could drive a car, you could ride a bicycle, you could walk. All those things do overlap for that use case. But as soon as the use case gets complicated, it starts failing very quickly. If you have to drop your kids off at school, the train's out of the question. If you have to carry a bunch of things, the bike's out of the question. If you're moving, instead of just going to work, you're moving across the country, you better have a truck. You're not going to do it in a car, and you're not going to do it on a bicycle. I mean, they very quickly don't overlap if you have a complex system. And in the industrial Internet of Things, especially, almost everything qualifies as a complex system, and so they just don't overlap. So you ask why they don't overlap. They don't overlap for the same reason you can't pedal a train. In theory, you should be able to pedal a train with enough low friction and gear ratios and a lot of training. But in reality, you can't really pedal a train. It's too heavy and not designed for that. It's a completely different world. So it's the best answer I've got for that. It's they're different. They solve different problems. They don't solve the same problem in different ways. That's another way to put it.
Okay. Well, what's the major difference as far as these different technologies
are concerned, what would you say is like this is the defining factor really that separates all of them?
The first major difference is what they send around. They all send data around. That's the only thing they have in common.
Yeah.
But how do they send that data around is the first major thing. There's really two levels. There's things that I do call protocols. We call it the transport level. MQTT fits into that. CoAP fits into that. They are just ways to send data. The data has no structure. So when you get the data, you'll get a bunch of bytes, and it could be names of people. It could be feedback control, sensor readings. It could be warnings about an impending explosion, and you would never know. None of those things are in that data, just a bunch of bytes. So you have to know what it is ahead of time somehow. And that's sort of the first, that's the transport layer versus the framework layer. The framework layer, you still don't know what they mean necessarily, but now I can look at the data and say, okay, it's got a name and an address and a, I don't know, a salary, and say, oh, this is a HR information. At least I know the name is a string and the address is a string with a number, which is the house number or something. I can now do something with that data. I don't know what it means necessarily. I don't know that it's an HR database or if it's a mailing list where I'm going to send advertisements. I don't know why it's there, but I know sort of what it is and I can read it. And the next level up, which we did not really look at, is semantic. Now I know that it's really a Christmas list, and I'm going to send you a Christmas card. So I have meaning to it. Yeah. But the protocols, the framework layer, are really only easy to use if you control the entire system. You're writing it all yourself. You don't have a lot of software in your system because it doesn't help you at all with sharing information. And importantly, because that data comes at you in whatever format it is, you can't easily switch between languages or processor types or operating systems. All that stuff's in the data, but you don't know where it came from. At the syntax level, now you can share it regardless of that. So the technologies that offer a real framework, which are the ones that we looked at, are DDS and OPC UA and 1M to M, really have way more than just a data definition. They have an entire type monitor, typing system, so that I can use whatever language I want, likely, and I can, interoperate now between software programs instead of interoperating between bytes. I had to know what was in it. So that's a very valuable step, and it really is the critical step for anything that we found in more complex industrial internet systems.
Oh, okay, yeah, interesting. Now, maybe just to linger on that question a bit, what do you think about Sparkplug for MQTT that try and enrich the MQTT payload?
Sparkplug and protobufs, and yes, there are many. That, so when we first looked at it, those things didn't really exist. If it becomes a standard, then it will take a step up and be more of a framework, right? If it's something that I can assume my other people in the organization, in the software system I'm using, are also using Sparkplug, then I can interoperate with them at a better level. Absolutely. But it's not really a now you have to agree on that too.
Oh, yeah.
It's not nearly as well controlled as things like a DDS or an OPC UA that has a standards organization and very clear specifications on exactly what data types are and exactly how those data types interact, even if they don't exactly match. One of the big problems in a distributed system is distributed systems evolve. So you can't really just update everything on one day, especially if they're complex things. It may take years to retest them and redeploy them. Even with over-the-air updates getting more popular, it's still very difficult to guarantee that all the components of a big system are the same version. And so one of the things the frameworks can do, DDS can do, I don't know if, I think 1M2M does it, I don't think OPC UA does it, is it allows you to match things that have changed a little bit. So the data structure, now that I know I've got this, this field with a name and 3 floats and whatever, and now I add another field to the end of it, DDS is smart enough to match those anyway. So if I send it to an old version, it'll strip that field off, and if the old version sends me something, it'll add something that says this is an old version, a flag or something, and then I can fix that in my code, but the fundamental system will still work. And we have systems in the field with 300 different versions of the same data type. And then it's a big ship. And the nice thing, you can pull into port and you can throw a new device on the ship or upgrade one part of the software, and it will match all the other. It has to be standard. And the standard is very specific about what will match, but as long as it matches, it will make everything work. And now you don't have to upgrade it all at once. And if you're trying to do a smart city or some really large system, we have a healthcare design for GE Healthcare is expecting 300,000 devices in a hospital. You just can't update all of those all at the same time.
Yeah.
It's only because a lot of them are going to be keeping people alive at the moment. You can't reboot it.
Yes.
But in reality, there's security issues and all sorts of things with testing. You can't upgrade everything at once. There's hundreds of different kinds of things in the hospital. You're all going to be ready to update at the same time. So those kinds of functionality aren't available to something like MQTT Sparkplug. So that did make MQTT more valuable, but I still don't think it's a good choice for a large distributed system, especially if it has to do the kinds of things that the other technologies do much better. All the technologies do something really well. And my favorite example, I call it the space. And if you're close to a planet in space, you should absolutely use that, or galaxy might be a better thing. You should use that galaxy's technology. If you're out in the middle of interstellar space, and there's a lot of interstellar space, and nothing really fits, well, now you can start playing games and writing your own code or making something fit. But surprisingly, most applications that we run into fit one of them reasonably well and hardly ever two. Never two.
Okay, that's interesting. Now, to alleviate the interoperability challenges, there's a somewhat common practice of using wrappers to sort of interface between one standard and the other, and you believe that doesn't work. Wrappers don't work, to put it in your words. Could you please elaborate for that?
There's many ways to do a wrapper.
Yeah.
Many reasons to do a wrapper. So if you're wrapping to make the API simpler, but not trying to change the fundamental underlying thing, that's fine, right? Almost all of our customers do that. DDS is very, very feature rich, and they don't want to do that, or they want to add their own data types, and you're going to use these data types, and DDS is handling underneath, but don't do anything else, and they write wrappers there. They write wrappers that add functionality. That's fine. If you're trying to write a wrapper that abstracts, whether it's DDS or whether it's MQTT, you're wrong, because you can only do the least common denominator in that wrapper, and the least common denominator in these things is just sending bits around or bytes around. So you might as well just use TCP/IP and old technologies, the raw technologies, because you aren't going to be able to use the power of any of the technologies if you wrap them. It's the same thing with trying to pedal a train, right? Let's see you write a wrapper that abstracts a train and a bicycle and tennis shoes, right?
Yeah.
And then, I'll say, okay, my use case is to go upstairs. You use your generic wrapper which could have a train underneath it to go upstairs in my house.
Yeah.
Right? The bicycle won't work. The train really won't work. The shoes would work fine, but you've written a wrapper that doesn't let me abstract any of those things. The only thing I can do is the least common denominator, and the least common denominator for a train and a bicycle and shoes is going short distances with no luggage, and you don't care very much how fast you get there. That's what you're going to be able to do with a wrapper. You won't be able to use the train, you won't be able to use the bicycle, and you won't be able to use your tennis shoes. It's the worst possible case.
Oh, okay, that actually makes a lot of sense.
Those kind of wrappers have been, in fact, it's one of our red flags when our sales force sees we're going to write a wrapper. We're going to abstract IoT technologies. They just don't know what they're talking about. They've never done it.
Oh yeah,
I've never seen it work. I've seen hundreds of efforts. I have never seen it work.
Oh, okay, yeah, makes quite a lot of sense there.
Right.
Yeah. Now, we moving on to just want to touch a bit on the industrial connectivity stack. I know you've already spoken about it. Like the fact that we already have some mature layered stack models, like your 7-layer OSI model, but yet you found it necessary to come up with the industrial connectivity stack. Like, why did you find it necessary, first of all, to come up with a separate industrial connectivity stack?
Because so first of all, the 7-layer model falls apart very quickly, even with an internet technology. Bottom 3 layers are great. Get to IP, everybody pretty much agrees. IP is the choke point that everybody agrees on. You get above those layers, and it very quickly becomes very difficult to put modern technologies into a single layer. The DDS standard, people ask, what layer is DDS? And the best answer is, well, it runs on top of UDP, but it's really sort of like UDP. It recreates TCP. So it's sort of a layer 4 technology, but it does data modeling. So, it's got layer 5 technology flavors to it. It doesn't have a notion of connections, so you can't really say it does connections, but it does support reliable sessions. So it's sort of a session layer. I mean, it really has flavors of 4, 5, 6, and 7 in it, all in one thing, and all the other ones do too. And when you try to map that to what's going on in an industrial setting with all the other complexities, it didn't capture what was important. What was important to us is that horrible word interoperability, what you're interoperable between. And we decided that we would, just try to do a model that's based on interoperability, and it worked great because the 7-layer ISO 7-layer model was originally done for interoperability also, but they were only trying to make a very specific type of system interoperate, which was terminal servers for mainframe computers, right? Okay, that worked. But it has a very clear definition of connections and sessions and all these kind of things that just don't exist in a much more dynamic and much more full of requirements world like industrial systems. So we had to write something new.
That's interesting. Now, so apparently there's not going to be one IoT connectivity technology for like everything. Instead, what we're going to see is like different subsystems that are based on different connectivity standards, and to cater for that eventuality, I think the IIC came up with the core connectivity standard architecture. Okay, could you like explain to us what the architecture is all about?
Yes. Well, first we have to start with, and I don't have an answer to this question, do we need this architecture? So the internet has a lot of power because it connects virtually anything to anything else. And people have found an amazing variety of things that make sense to connect that you would have thought of when you designed it way back then. So maybe there is that. But today, you know, people talk about needing to be able to connect the power grid to a hospital operating room so that if the power grid goes out, you can keep operating. But in reality, that's probably not going to happen anytime soon. And to also want to connect that to the factory across town that's building, you know, suspension parts for a car is just why. So first thing is there a demand for an architecture to connect something together? I don't really know that. But if there is a demand, right? And there definitely are cases where there's a demand. Like we run into a demand between DDS and OPC UA, but typically for very different applications, but they do need to talk with each other because you know DDS can handle much larger data environments. You sort of need a gateway between them. And if those gateways can be standardized, then you can build a nice architecture that you can pick and choose the right technologies for the right pieces. And so we sort of did two things. We looked at, are there some accepted and reasonably well adopted, at least in one market, technologies that are both sort of, you know, well defined and have enough users that, you know, they're going to be around for a while and cover the application space as best we could. And we essentially came up with 4 of those. Not claiming they're the only possible 4, but there's at least 30 or 40 domain technologies out there, and you can't build, if you try to build standard gateways between 30 of these things, that's 30 factorial gateways. That's a very large number of gateways. You'll be writing gateways to end all time. With 4 technologies, we only need 12 gateways, or, you know, really only, so you get 3 gateways. Each technology needs to talk to 3 other technologies. It's doable, right? You don't need that many gateways. And a lot of them sort of already exist or are in the process of existing. So for instance, one of the technologies, HTTP, you know, web services, and DDS already has a standard gateway for that. I know the DDS stuff better. And DDS to OPC UA is something we've been working on, and now there's a standard out for that. And we have implementations of that. You know, to 1M to M, we haven't had that demand yet. Maybe when 5G comes along and makes applications that work with DDS for that, it will make sense. But it definitely has the potential to build a connection to the other frameworks. So, you know, and those 3 make DDS now capable of talking to everybody, and the other ones all have them also. I suppose you only need 6 different gateways. That's what. I'm a little confused because they're trying to add another core technology, which makes more gateways.
Okay, so currently you've got 4 core technologies for your.
Currently, original IICF has identified 4 core standards and proposed standard gateways between all the pairs of them, and then, you know, and then you can have you know, specific gateways to anything else. If it can connect to any of them, it could in principle connect to all of them. Like I said, I don't know if there's really a demand for this. We're still trying to figure that out. But I think there will be over time. These technologies aren't going away. If only for legacy integration purposes, there are going to be demands for gateways between these things. For things like, connecting to field buses,
Yeah.
Modbus, Profinet, not Profibus, Profinet. Those kinds of things you need gateways, but you probably don't need them to all the standards. Because connecting it to one M2M, which is designed for the cellular network,
Yeah.
why would Modbus need to connect to that? So if you can just connect that into DDS or connect into OPC UA, now you can, and it can connect to the web over HTTP. Well, now you've got the ability to do that. So that's the whole idea, is to get rid of the n squared. I suppose not 30 factorial, 30 squared, but get rid of the n squared problem with gateway explosion and put together a clear, simplified architecture for that. But it's still 10, 15 years out. Today, you don't want to wait for all those gateways. You need to go choose the best one of these architectures to work with.
Oh, okay. Yeah, it makes a lot of sense there. Now,
And
one of the connectivity technologies that I find so fascinating is a data distribution service, or DDS, and I'm like still trying to wrap my head around all the concepts of DDS. But can you like give us like sort of like a very brief explanation of what DDS really is?
yeah, so I've been working hard on trying to make this more understandable to people, because if you read the standard, which is, I don't know how many hundreds of pages of dense technical stuff, it talks about things like a global data space. If you have to put DDS into a box that you can understand, think of it as a very intelligent distributed shared memory. But the way I like to explain it makes more sense. DDS is a virtual, it gives you the virtual environment that is a fiction. It's not true, but it's fiction. It seems like all the data in the entire system is right. If you're writing an algorithm, all the data is in your local memory. It's in your algorithm. If you're writing a sensor, it's writing, all the data is in the sensor. I can write to that data and everybody else gets it. If you're writing an actuator or some other thing and you need data, it's right there in your local memory. And so it looks like all the data, and we have systems, 300,000 devices, a whole fleet of autonomous vehicles that have LiDARs and radars and operators that are monitoring the system. If you're one of those operators, all the data of the entire system is right there in your algorithm or in your workstation display. It's not true. It's not possible, but it acts that way. And so you're just, as an application developer, are reading and writing what looks like local memory. That's DDS. So people think it's publish, subscribe. Well, it sort of is, but it also supports all the other patterns. It supports queuing and it supports request reply. And it's just not true that it's only published. What's important about it is it's all about the data. The data, it's all right there for you. And the way it really works, okay, it looks like it's all there. It's not really all there. If you, for instance, need to read something 100 times a second and you want it to be in your data, in reality, it's living on devices all over the place. You just tell DDS, okay, I need this updated 100 times a second. And here's what it is. Here's the data. And DDS will go out and find anything that might be able to produce that for you and give the specification. And the specification can be pretty complicated. It's not just 100 times a second. For instance, I want to know, I'm building an autonomous vehicle. I want to know anything within 200 meters of me that's moving towards me at more than 2 meters a second. That's my specification, right?
Yeah.
And I can send that to all the sensors on my vehicle, or even someday to the cameras on the street or whatever. And anybody that has that information now knows that I want it. And not, they don't, their application doesn't know. Their application is just writing what they know into memory also. But the DDS on their application now knows that I want it, and it will send it to mine, and it will get it to mine guaranteed exactly to be in my memory when I'm going to go read it 100th of a second later. And so I go and I read it and I say, oh, there's a pedestrian that's walking across the crosswalk in front of me at more than 2 meters a second, and it's coming towards, towards me might be some collision path or something. I now know that's there, and then I can do something about it. So that's the magic of DDS. It's finding things in the data space and delivering it to you. That's why data distribution survey. If I could rename it, it'd be data centric architecture. It really is data centricity that's important, much more than distribution, and certainly much more than publish subscribe. It's really getting the data you need in the right place at the right time.
Oh yeah,
That's what DDS does. Nothing else does anything close to it. Every other technology has the concept of active things, clients and servers. The data lives on the server. You're a client, you get it from the server. Or messages, you send messages. Where do you send messages? Well, you send it to some active thing, either another application, or you send messages to a queue. Something that has to exist, right? One of the nice things about having the data in my own memory, I don't have to know you exist. I don't know anything else exists. I just read it and write it in my own memory. Now, if I ask for it 100 times a second and it doesn't show up, that's an error condition. I don't know. I don't have to even know why it didn't show up, although there are ways to find that out. But the condition is the data is not there. There's a failure in some form. The communications are down, or there's no sensor out there, or maybe nothing ever even matched my specification. All of those things are errors, but they're not something I can start reading it immediately. And nothing happens. There's nothing there. I know that that's not working. It also has a very interesting trick of something called liveliness. So if I know, for instance, I'm running an airport and there's 9 approach regions to my airport, and there's multiple radars or whatever the sensors are watching for airplanes coming into my airport in all 9 of those regions, I can say I need liveliness guarantees on all 9 regions, meaning that if there's no data from them, it doesn't mean the radar's down. It means there's no data. And what DDS is doing then, and when you say liveliness, you should say, like I need DDS to guarantee that this data is not more than 1/10 of a second old, essentially. And now DDS is just going to, if that radar isn't writing data every 1/10 of a second, even if there's nothing in that data or nothing I care about in that data, maybe I only want airplanes within 5 miles descending and coming towards me, right? That's all I care about below some altitude. Even if there's nothing there, at least I know it's alive. I know the radar is working. It's very different to have no plane there and have no sensor there. It's a very, very different condition. So DDS handles a lot of the complexities of interactions between all of these systems much more easily, because it has an ability to be data centric.
Oh yeah, that makes a lot of sense actually, because I remember reading somewhere where it was saying with DDS is like you are accessing data from the future, as opposed to something like accessing data from a relational database where you are accessing data from the past.
Right. So yeah, a database is also a data centric architecture, but all the data is old.
Yeah.
So a database has, a database is become absolutely required for every business system. You wouldn't dream of building an auto parts store without a database. You wouldn't dream of building a 1-person food truck without a database, right?
Of course.
I suppose you could do it, but but it's all stored data. So I can search my auto parts store for alternators for a 2005 Chevy, right? How much they cost, and when do I have any inventory? That's called a slice, right? You search for that, and then you can say things like, well, there's none. Then you can do things with it, like I don't know, add it to a list of a cart, or see if I don't have any, when they're going to ship. All those kinds of things can be done with that slice. My slice with the airport is also a slice, but it's future information.
Yeah.
Because that data for the parts has to already be in your database when you search. But I can search for, airplanes within 5 miles, below 5,000 feet, descending and coming towards me in the future.
Yeah.
And if one of those shows up, I need to know about it in 1/10 of a second. Well, that's also a slice, but it's a slice that hasn't happened yet. It's very similar to a future database.
Yeah, that's very interesting. Maybe to put it into perspective for some of our audience here, can you compare between OPC UA and DDS, maybe to try and put it into perspective? What's the major difference between OPC UA and DDS?
Yeah, so first of all, there's nothing more important in an architecture than what abstraction it offers. Okay, so DDS offers this data-centric abstraction. All the data you want is available to you with a very, very specific, it also has data type. So, if I'm writing code, I know the type of data I'm talking about. I know it's a string that's called name, and then floats called, floating point numbers called X, Y, and temperature, right?
Yeah.
I don't know what that means, but I do know what they are. But it also has, it's data centric, and I know what I can do with it, things like that. OPC UA is so that's the DDS abstraction. The OPC UA abstraction is object oriented. It's fundamentally object oriented. Object oriented means you have objects, and objects interact with other objects, right?
Yeah.
So in DDS, you only interact with your data. You don't interact with anything else in the world. OPC, you have objects interact with other objects, and there's very specific things those objects can do with them, and those things they can do are called methods. And so objects can export methods and do that. And then they have the next layer of abstraction is to have those methods. You have to find the objects. The objects may actually be presented to you on a server somewhere, and you have all these server interactions. So it's a completely different abstraction to start with. But what comes down to, like I said, they all grew out of different things. OPC UA's fundamental idea is to offer, to model a system as what they call devices, things, conveyor belts or curing ovens or something like that are part of a system. And you talk to the curing oven and set its temperature and things like that. And they have very clear definitions of what devices are, and things called companion specs. So you can affect interoperability between curing ovens sold by different vendors. That's their main goal, is to free the end integrators, factories or whatever, from being dependent on a single end integrator and a single parts supplier, vendor. And so it's got standard device types, and it's got, read write variables and all those kinds of things that make it possible to mix and match those things and build a system. There are software components also, but they're also well defined. They're usually historians and HMIs, things like that. There's not a lot of other software technology or architecture, because it's really not used by software architects. Most of the code in OPC UA systems are vendors writing devices or building devices, and most of the end integrators are not programmers. They're people in factories building, assembling parts, not writing a lot of code, not a lot of custom code. DDS completely different. The end users for DDS are almost all programming teams. There's virtually no device software out there, because DDS models devices as software interfaces. So It's not where you start. So they're really different. They're different user sets. They're different ways of thinking about how the system is put together. Different applications. One is designed really for integrating intelligent systems into large networks of things. That's what DDS does. And the other one's really designed for mixing and matching devices. And if you walk around trade shows, you'll see that, right? You
Yeah.
walk around a trade show, you'll see walls of devices in the OPC UA booth that all have OPC UA running, with the obvious implication that you can now interoperate between those devices. And you'll see absolutely no talk about, or very little talk about, how you write software for that wall of devices. It's just
Yeah.
maybe there's a GUI that you can put it together. If you go into anybody selling DDS, you'll see virtually no devices. What you'll see is systems. You'll see autonomous vehicles and power grid systems and all these things that are put together with DDS, but not at the device level, at the system level. It's strikingly different if you think of it that way. They don't compete.
Yeah.
We don't. I've almost never seen an application where you could choose one or the other logically and expect it to work. In fact, if you really look at it, they're diametric opposites way more than they are similar.
Oh yeah. Yeah. Now, what do you see as the future of connected IoT, and to what extent do you think 5G is going to affect that?
5G is an interesting new technology. I think it's a pretty low level technology from our point of view. I'm still struggling along with the rest of the world what 5G can do that 4G can't, to be honest with you. Until it's really truly reliable enough to base the safety of a system on. You can't really drive a car with it or something like that. You could drive it for a while, but you're going to need all sorts of backup systems. You need those backup systems for 4G too, and it's probably fast enough to do video monitoring remotely or something like that. So, I do think it will get there, but it's a long ways before 5G really changes the way the world can run many different things. So it's definitely an exciting future, but it's a while before you can use it in a generic setting.
Oh, okay. All right. Okay. So now to round things up, I want to talk about your company, Real-Time Innovations, and the Industrial Internet Consortium. So first, could you please tell us what Real-Time Innovations is all about?
RTI we're the largest provider of architectural software, of any kind of architectural software for smart machines or real world systems. We're actually a pretty good sized company compared to the others in the market, selling other things like OPC UA or MQTT or any of those kind of things as software. We have our biggest markets are defense market and automotive, or transportation, I suppose, in general. We're in over 250 different autonomous vehicles designs, and then a bunch of other research vehicles. Those are all in some production track things. A lot of those are flying things. We sort of started out in the flying vehicle world, but our hottest new markets is urban air mobility, flying cars. We have a lot of ground vehicles as well. We do power systems, almost all renewables, hydropower, and wind power. We're running the largest power plants in North America and balancing systems for the grid and things like that. Medical, we do a lot of medical stuff, connected medical devices, medical robotics, hot market, lots of stuff going on there. We're very involved in all of those kind of things. And I don't know, our product has DDS sort of at its core, but we do many other technologies around it because really DDS is an architectural standard. It's not really a product, even though we named our product that. I'm probably going to change that at some point, but it is just the core, and around that core, there's an awful lot of different pieces ranging from routing services and scalability helps and tools and all sorts of things that make it possible to build a real world system. We make all this kind of stuff really work in the real world. We're way more experienced than our other companies in making stuff work.
That's
That's my quick.
That's very interesting. Okay, now, so lastly, you are part of the Industrial Internet Consortium Steering Committee. We've already spoken about the IIC, some of the IIC initiatives at length. But what I would like to find out is what are the primary aims of IIC, and how are you doing so far?
So first of all, I stepped down from the steering committee. My companies are growing too fast for me to do that anymore. I'm CEO of that company, so I did that for 6 years. I just stopped doing that this year. So, but the IIC is the place where everybody sort of gets together, all the different markets. It's always been a very horizontal organization going after sort of defining this Internet of Things, industrial Internet of Things, and the largest organization doing that in the world. Its real goal is to put together architectural specifications that many different industries can use to accelerate what they're doing and try and make this vision come to life sooner. It's a hard job because everybody wants to push it in their own directions.
Yeah, because
but I think it's it's an important thing to be doing.
Oh, okay, yeah, that's interesting. Okay, that brings us to the end of our conversation. Thank you so much, Stan, for joining me today.
Yeah, well, thank you. I'm sorry I talked too long at the beginning because it would have been nice to go into a little more depth at the end, but that's okay. I get excited about this stuff.
Well,
I really do see the future of connected systems as amazing. I think it's our planet's best chance to improve a lot of things, from global warming to some better power systems, to autonomous vehicles, to safer systems. I'm actually pretty excited about some of the fish farming technology, which can make very low cost, high volume sources of protein available to the world without damaging the oceans. That's exciting. I just see the ability of us to really use intelligent, smart things as transformational. Historians will look back at our time and wonder how we got by without smart things.
Yeah.
How people got by without electricity or engines or wheels or fire. I mean, it's an absolutely fundamental new thing, and I'm really excited to be part of it. I think it'll still be new 40 years from now.